This video is going to be about the second of our named distributions. So we're first going to describe a new feature of distributions that we've kind of been talking about, but we haven't ever specified with any sort of sincerity or in any kind of concrete way. So the first point of this video is going to be distributions have parameters. And then we're going to jump into the binomial, our second named distribution in this course. If you want a good reference for the binomial distribution, I recommend section 3.2.2 of our textbook Biostat. You don't so much need the formulas in this class, so much as you need the idea of what this distribution is doing. Okay, so here we go. Our first point for this video, distributions have parameters. We're getting to the idea that the world of statistics is trying to make statements about the population. And we are formalizing with random variables the idea that distributions are what describe the population of interest. In the world of statistics, we actually theorize that there is a mathematical formula describing this curve, and this curve is the distribution itself that describes the population. So really what we're doing in statistics, more so in more advanced courses that have to do with a lot of calculus, we're identifying a population with a mathematical formula that we call a distribution. And these distributions have population parameters. That is, they have characteristics that describe the population of interest. For instance, there is a population mean mu. It's always generally written with the Greek letter mu to describe the population mean. And what we say is, if you're interested in all US adults' heights, then there is a population of US adults, and if you made a density plot of all of their heights, it would look something like this, oddly enough, and there would be a mean of all US adults' heights, as if you could get your hands on all US adults, add up all of their heights, and divide by however many there are. That's what this population parameter mu is theoretically equal to. And moreover, there is a population parameter for the standard deviation that we call sigma. That is this kind of like average squared distance from the mean value that translates something to like how wide at about the height of the shoulders of this distribution is the population distribution. How wide is that thing on average at about that height? We can't say how wide is it in the tails because those tails technically extend off to negative and positive infinity. So we try to measure height somewhere about those shoulders. If you've had calculus before, it's really at an inflection point of those curves. And so in the world of statistics, what we do is draw random variables from that population to form a sample, and then we estimate the population mean with whatever observations we have in our sample. We add them all up and divide by however many there are. I like to call that estimate mu hat, but often people will call it x bar. X bar doesn't really mean anything to me because I don't understand how x bar and mu are symbols that should be related at all. But you will see in the book Biostat and outside of this class, x bar is the sample mean used to estimate the population mean. And similarly, from our observed values, we can estimate the population standard deviation. So what we've been doing so far is going about naming these distributions and showing, at least in R for now, how we can estimate these population parameters. And we'll do that again for the binomial distribution, just like we did for the Bernoulli. For the Bernoulli distribution, we estimated the population parameter P, that is the probability of observing some success. For the binomial distribution, we're going to be able to estimate a population mean. but it's going to be related to the Bernoulli in very specific ways. So let's detail how the binomial distribution is related to the Bernoulli, and then we'll get into R and show something like more specific examples. They'll be fake, but I think you're catching on to the idea. So binomial distribution is the sum of k Bernoullis. Well, what does the sum of k Bernoullis mean? I'm going to try to keep these examples away from coins so as not to confuse these two. I'd like you to have like two separate mental models for these two different distributions to try to help keep them identified well. So imagine we are trying to compare alleles of the human genome. That is, we want to match up, let's say, k equal to 5 base pairs between human A and human B. Okay, so let's just make up some sequences. A, C, G, T, A. A, T, G, T, A. So in this example, we have k Bernoullis. We can think of it as like, do the base pairs match at the first site? If yes, indicate with a 1. If no, indicate with a 0. Do you see how we're creating a Bernoulli out of the question? Do the sites between these two different humans' alleles match at each of the base pairs? At the first site, they match, so we give it a 1. There's one Bernoulli. At the second site, they do not match, so we give it a 0. At the third site, they do match, so we give it a 1. Fourth and fifth sites match, so we give them 1s. The sum of these 5 Bernoullis is equal to 4, and this is a binomial observation. That 4, the sum of k Bernoullis. But the binomial is so general that we don't actually care how many Bernoullis we're interested in, as long as we know ahead of time there's k of them. Okay, so let's fill in the rest of the details of the binomial distribution. Each Bernoulli, each of the k Bernoullis has probability p of 1. So all of the Bernoullis have the same probability p for, in the case we just had, matching the base pairs at a specific site. Okay, sum of k Bernoullis, each Bernoulli has probability p of 1, and the Bernoullis are independent. We don't spend too much time on this phrase in this class. We'll just generally say independent means the first base pair and the second base pair have nothing to do with each other. They are completely independent and separate outcomes for whether or not the first base pair has anything to do with the second base pair. There's no relationship between that at all. Now, in the world of genetics, I believe we would assume that the genomes for whatever animals we're trying to like match base pairs of are in equilibrium is the idea you would have there. As long as the genomes are kind of stationary, then we can assume that the base pairs are independent, don't have any correlation between whatever you observed in the first base pair for whatever you observed in the second base pair. So the binomial here is described like this in a very general way, but you can imagine how general the Bernoulli is. You could have very specific examples of a binomial as well. All you've really got to do is imagine you are looking at Bernoullis in batches of size k. So let's just write that down. My next example is still going to be kind of general, but I think the phrase will help you better get the understanding of a binomial. A binomial distribution describes Bernoulli's in batches. Let's rewrite the word batches so you know what I'm saying here. Batches of size k. So theoretically, you could have k flips of an unfair coin, and that would describe for us a new binomial distribution. Okay, let's jump into R, and we can now get a better understanding of the function R binom. What it actually means is randomly generate observed values from the binomial distribution. And the same thing goes for the first argument. How many observed values do you want? The second argument to the function R binom is what I call K. It's the size of your batch. So we could say, like we did before, we have size 5, and let's go with a probability of success of 0.8. I don't know, maybe the base pairs are likely to match somewhere along the way. So in this case, we have 3 observed values. Each of the values is the sum of 5 Bernoullis. So theoretically, all 5 of the Bernoullis could take on the value 1, or all 5 of the Bernoullis could take on the value 0, or all 5 of the Bernoullis could take on any integer in between 0 and 5. The first of 3 observed values had 4 of the 5 Bernoullis indicate 1. Okay, let's say this again. The second of the 3 observed binomial observations saw 3 of the 5 outcomes of the Bernoullis successful. Okay, last one, here we go. The third of 3 observations observed 4 of 5 successes, where the probability of each success we have dictated to be 0.8. Okay, let's try. Look, you can change this up however you want. Let's keep it small for now. And I encourage you, stop the video now and try to figure out, based on the example I just gave, what this line of code is doing and why it generated numbers like this. First, explain how many numbers there are, and then try to explain to yourself why the numbers we observed can be anything from 0 to 10. Okay, now let's try to estimate the population mean of a binomial. So we're just going to generate, 5,001 binomial observations that are like, let's say, 10 coin flips in each batch of an unfair coin that has probability of success of 0.8. So there is a whole mess of data, and I'm reminding us / encouraging us to estimate the population mean by calculating the sample mean on a bunch of observed data. So here, I will call this mu hat, because we are estimating the population mean mu. Now what we get out is 0.798. If you're starting to see that that's somehow related to this 0.8, you're right. That's a really good intuition. Let's make sure that intuition holds if we sample a crazy amount of observed values from this binomial. And indeed, we seem to be encroaching on something related to this 0.8. Now, if you think back to the meaning of a binomial, it's the size, the size of your batch, K, independent Bernoullis, where each Bernoulli has the probability of success, P, here. So really what we're after is 10 Bernoullis, where each Bernoulli has a probability of success, 0.8. And indeed, that's where our population mean for the binomial is coming from. The highlighted value here is the population mean for the binomial. You can see with a ton of observed binomial observations from the appropriate population, we estimate the mean quite well. I'm going to leave it to you all to give yourself as a new example these 3 lines of code where you can change the number of observed values, the batch size, K, and the probability of success, and see if you can generalize the population mean formula for your new example. And the way you can double check is if you generate a ton of observed values by estimating the population mean, your estimate should be close to whatever your new formula gets you for the exact population mean.